so this is the second part of voltaic cells. Now you've hopefully watched through how to use the reduction potentials table. Now we're going to start going and using all of these rules that we discussed to determine what in fact is happening to the total voltage. And that's where we're going to look at this next section. All right, total voltage. We've got a couple of things that we're working with, right? So we're looking at this. You might remember doing this in the experiment where you set up 2 half cells. Again, each half cell holds 1 half reaction. So 2 halves will make a whole. And what you want to notice is you want to see what has been placed into the half cell. So we've got chromium solid and chromium 3 nitrate. That means that the reaction that we're going to be looking at will be something between chromium and chromium 3 ions. What's going to happen to the nitrates? They're going to spectate. The same is true in the other half. We've got copper, and you can see we also have copper 2 nitrite. The nitrate is also going to go ahead and act as a spectator, so we're really looking at copper versus copper 2. You can see that the corresponding metal sits in the solution. So you have chromium in the chromium solution, you have copper in the copper solution. If we wanted to change that up, we could, and let's talk about that in a little bit here. All right, so the first thing that we're going to do is we want to create this into a voltaic cell, which means that our combination of the chromium and the copper together need to create a electrode potential that is positive when you add the 2 values together. So one of these, again, needs to be reduced. The other one needs to be oxidized. So let's go straight over to our table. In our table, we're going to be looking for chromium and chromium 3 and copper 2. Okay, so I see a couple great things here, right? Copper 2 and copper is this one. All right, sorry about that. So we've got a nice copper 2 to copper solid as 0.34. So copper 2 to copper solid has a voltage of 0.34. All right, let's look at the next one. Again, looking for chromium and chromium 3. And again, don't accidentally pick this one because that's chromium and chromium 2. So we're going to take this one now. All right, so chromium 3 to chromium is negative 0.74. Whoops. So negative 0.74 is that voltage. All right. You can tell then between our 2 options, both of which are reduction, gaining electrons, the one that has a voltage that is positive, or at least more positive, is the copper ion reaction. That tells us since this is positive, this reaction is going to be reduced exactly as written by gaining 2 electrons. It also tells you that your chromium cannot be reduced because of the negative voltage. So we're going to have a chromium solid turn into the chromium ions, meaning that it'll be oxidizing 3 electrons, and it will have a voltage now, because we've reversed the reaction, of a positive 0.74. Okay? These are now going to be our 2 half reactions. So let's get rid of the work that we were looking at, right? We don't need this anymore because, again, we've now flipped the reaction to make the chromium to chromium 3 reaction be oxidation, and we're leaving the copper 2 to copper to be our reduction. All right, we want to do a couple of things then. We're going to go ahead and we want to write out our balanced reaction. So now here's our chromium to chromium 3, and it's releasing 3 electrons. You've got your copper 2 ions that are actually gaining 2 electrons. And now you're making copper solid. So just like our work with balancing reactions, what you're going to do is you're going to look to see that all of the electrons get canceled. So since we have 3 electrons in chromium and only 2 electrons in copper, again, we want to make sure that we have the exact same amount on either side. And so we're going to go ahead and we're going to multiply each reaction by the lowest common number. That means that this is going to get a 2, 2 for 6. And copper, we're going to multiply by a 3 for a 6, a 2, a 3, and a 3. And now we see our electrons will cancel. We also see we are not changing the voltage of either one of these because we've already taken care of all of that by rearranging them. And again, because voltages are not dependent on how many electrons get passed, just that electrons are continuously flowing. So our final reaction is going to be 2 chromium solids plus 3 copper ions to yield 3 copper solids and 2 chromium ions. It also means that our voltage will just add directly together. So our voltage, which is now the total or the cell, is positive 1.08 volts. All right, so that's a lot of information. This is now the reaction that's occurring within our cell, so that we're including both of the halves. We also have an anode and a cathode that we can now define. So an anode is the electrode where oxidation occurs. Since the oxidation was over here with the chromium, that's going to make our chromium metal the anode. So this chromium is now the anode. Notice what happens is if you're trying to remember who's who, oxidation and anode both start out with vowels. Since the reduction happened on the copper side, that now means that our copper is going to be the cathode, because the cathode is where the reduction is going to occur. Notice if you look at the cathode and the word reduction, each of those begins with a consonant. So again, to sort of help you remember who's who, that's going to be useful. All right. We're now going to go ahead and look inside of the cell a little, so let's zoom in even a touch more. And because the chromium was going from the solid to the ions, what you're going to see is that the solid is going to start disappearing a little because it's going to be making all of these chromium ions. Since the copper ions were turning into copper solid, you're going to end up seeing that these copper ions from the solution turn into the copper solid itself. And so that is going to end up getting thicker. All right, so a decrease in size of the chromium metal, but an increase in size of the copper metal. As the reaction takes place, since the chromium is where the oxidation is occurring, you're going to see the loss of electrons flow through the wire. So the electrons flow through. As they do so, you're going to see the light bulb will pop on. And if instead you had a voltage meter, you'd see that all of a sudden you had a voltage occur. Then the electrons are going to flow back down into the copper electrode, which is again where reduction is going to occur. So the copper will find the ions themselves, they'll join up with the electrons that are coming into it, and then end up on the copper solid itself. Okay? And then the other thing that we want to look at is what's going on with our salt bridge. So again, your salt bridge could be anything that is neutral. You already saw that we used ammonium chloride. That's a nice neutral salt. It is neutral in the sense of redox, not necessarily neutral in the sense of acidity. So let's pick something that's neutral in the sense of acidity also. That might be like sodium nitrate, right? Sodium ions come from They're the conjugate of sodium hydroxide, strong base, that makes the sodium ions neutral. Nitrate is the conjugate of the strong acid, nitric acid, so again, it's going to be neutral. As you can tell from what's occurring here, as more and more chromium breaks into its ion form, this solution is going to become very, very positive. The object of the salt bridge is for the nitrate ions then to come into that solution. And because the nitrate ions are negative, we're going to reestablish neutrality within the solution, meaning that we don't want a buildup of positive or negative charges. So the nitrates will flow out of the salt bridge. That will allow this solution to remain uncharged. And because that solution remains uncharged, it will allow the electrons to continue to flow through the wire. At the same time, with the copper ions, because they're disappearing into the cathode, you have all of these nitrate ions building up. So all of these nitrate ions are just hanging out in solution, and you're getting more and more of this electrode being negative. Because of that, will flow from the salt bridge some of the sodium ions. And so now the sodium ions will again reduce the positive and negative charges that are building up because of the nitrate ion being left by itself. So that's how the salt bridge works, is it's always trying to neutralize the two solutions in terms of their charge. And because of that, you need to have something that's not going to react as a side reaction. So any salt that's made out of spectator ions is going to be a perfect salt for the salt bridge.